Hi everyone, I am Jackson Jacob Sakuria, an exchange PhD student in Photonics Research Laboratory since IASC from Integrated Photonics and Application Center, RMIT University, Melbourne, Australia. Today, I am going to present my work on polling-free second-order nonlinear waveguides in lithium niobate and insulator using bound states in the continuum. As the topic says, I am working on second-order nonlinear process. So before going to the work, we should know why this second-order nonlinearity or Kai2 process are important. For that, the simple answer is like, if you have to manipulate light, generally we use a nonlinear process. In those nonlinear processes, Kai2 nonlinear processes are the efficient ones. For example, if you have to increase the data transfer speed in an optical fiber communication channel, you need a wide spectral source, which can be made possible by using the second-order nonlinear process, as well as it follows the application in quantum optics and many other fields in the current gen. When you think about Kai2 process, it is material dependent, so you have to select a perfect material to get really good conversion efficiencies, as well as we work on an integrated photonics platform. If you see the conventional data centers, you can see really large equipments that consumes a lot of space and a lot of energy. By using this integrated photonics platform, we can shrink the size of these devices to the size of your fingernail with much better performance and really less energy. By keeping all of these in mind, we have to choose the integrated photonics platform with really good Kai2 nonlinear process. When you check the current available integrated photonics platforms, silicon and silicon nitride are the widely used ones. But both of these materials don't possess any Kai2 properties, which leads us to think about lithium niobate based, aluminum nitride based, and gallium nitride based platforms, where we can achieve really good Kai2 properties. In those lithium niobate based platforms are matured ones, as well as they possess really good Kai2 property and many other properties like we can achieve electro-optic modulation by using the same material. This leads us to select lithium niobate based devices for our application. So we chose lithium niobate on Insulator platform for our work. By this, we can achieve really good second order nonlinearity. And as I said earlier, we can do electro-optic modulation and many other things because of the special properties of lithium niobate and integrate them into the same chip. As well as this material allows us to work on a wide range of wavelength because of the wide window it possesses. This material confines light really good, because of which we can get really low propagation and insertion losses. By keeping all this in mind, we chose the Niobate Insulator platform for our work. The next step is to show a really good conversion efficiency by using this Kai2 material. So that the simple process is to do a wavelength conversion, where if you send a fundamental wavelength to a nonlinear crystal, it gives out the fundamental wavelength as well as a frequency double wavelength coherently. In bulk crystals, we can send light through a particular plane of this nonlinear crystal, and we can achieve this phase matching. But when you use a thin film platform like lithium hybrid insulator, you have to use either a quasi phase matching or a modal phase matching technique to achieve really good conversion. In this, people had shown by quasi phase matching about 2,600% of conversion efficiency, which is high till the date. And this kind of device are generally known as periodically poled lithium niobate, where they invert the domains of the material to achieve this phase matching between the fundamental and the second harmonic mode. But the problem here is like the fabrication is really complex, as well as the repeatability of the devices are question mark. So this leads us to think about another process known as modal phase matching, where you can achieve phase matching between the fundamental and the second harmonic mode by engineering the geometry of the waveguide. But what we generally observed is like people were getting really low conversion efficiency by using this modal phase matching method. So we thought of like taking this modal phase matching for our work, but we have to improve the conversion efficiency. So the first thing what we had done is like certainly people had etched the lithium niobate which is a really complex process, as well as we can have large losses because of the scattering loss from the sidewalls of this lithium niobate after etching. So we thought of like avoiding this. So in some literature, we had seen people using a polymer on top of lithium niobate so that they do not etch down lithium niobate. This is like promising. We thought of like using this idea in our work. As well as when we had seen people generally people get really low conversion efficiency because of low modal overlap between the fundamental and the second harmonic mode. So we thought of like we should overcome that too. As well as the other fascinating thing that we observed is like people are using Z-cut lithium niobate, which can access only the D31 nonlinear coefficient, which is 7 times lower than the D33 nonlinear coefficient that you can access if you use the X-cut lithium niobate on insulator. So we decided to use an expert lithium niobate to access these D33 nonlinear tensor, as well as we had loaded silicon nitride on top of lithium niobate so that we do not etch down lithium niobate. Silicon nitride processes are well defined, so this will make the fabrication much more easier. To overcome the less modal overlap issue, what we had done is like we had choose a vertical mode in second harmonic wavelength so that in the lithium niobate region, we can get really good modal overlap, which contributes for the conversion efficiency. By doing all this updation, we got a really good conversion efficiency of nearly 400% in simulations, which is really good. While doing these simulations, we caught with a really interesting phenomenon. Like if you take this mode, the higher order mode, you can see that the effective index of this second higher order mode is really low than the effective index of the fundamental mode in the cladding region. You can see that in from this plot, which means it like if the effective index of the core mode is less than the effective index of the fundamental mode in the cladding, the mode tends to leak through the cladding region. But it doesn't have to happen in our case because we use bounded states in the continuum, which means that at particular width and thickness, we can achieve a destructive interference among various loss channels, which will lead to really tight confinement of the mode in the core region with a very less loss or with less leakage. So now we have to achieve phase matching as well as we have to achieve bound states in the continuum to get really good conversion efficiency and a low loss waveguide. So for that, what we had done is like we had varied the silicon nitride thickness and width of the silicon nitride thickness and checked up to what dimensions we can achieve this phase matching as well as loss. This will help us to get an insight about the fabrication tolerance too. By seeing this plot, you can see that if you the fabrication tolerance or after a 20 nanometer width, these devices gives either a low loss, either a really high loss, or there won't be a good phase matching. So this seems to be like not that much promising because fabricating a device with 20 nanometer tolerance is really tough. But when we had checked by varying width as well as for different wavelengths, we found that if we vary the width of the waveguide also, we can achieve phase matching and low loss at different wavelengths. This becomes really promising. So we had gone ahead with fabricating these devices. So the current stage is like we had fabricated these devices and characterized them. Currently, we are testing these devices. Hope that we will get really interesting results in the coming days. So stay tuned to our channel. So the conclusion is like we were able to get really efficient second harmonic generation by using bound states in the continuum, as well as we were able to get really good conversion efficiency of about 400%, which is really great. As well as we were able to add and devise on the existing silicon nitride loaded lithium niobate and insulator infrastructure, enabling applications in optical communication, quantum photonics, and sensing. So thank you for watching this video. If you are interested in integrated photonics platform, stay tuned to our channel. If you like this video, Like, subscribe, and share this video to your friends. Once again, thank you. Have a nice day.